Yes. Okay, so we start by mapping Axion experiments throughout the world. Here we see ongoing experiments, experiments that are planned, and also experiments that are now going to phase 2 or generation 2 experiments in which part of the experiment are being improved. Okay, so not a new concept, just scaling. And a typical example in these experiments is increasing the magnets that are involved in this search. So you see that all I have to update this map by adding a few experiments. So there's a new experiment in Taiwan, this cavity experiment, and then we had to add also the alpha collaboration experimental effort, which is everything okay? This is old style. Can I use this? I leave that to you. Super, thanks. Yeah, this is exactly what I needed. And I was saying that you see this map, but please consider that things are changing very rapidly. It's really, from the experimental point of view, it's a field that changes very, very rapidly. So there are new concepts that are coming out, and people, experimental groups that are trying to realize these new ideas. And new concepts come, as you will see, very, very useful, very interesting when current experiments encounter limits that are intrinsic, so that cannot be overcome just by scaling. Okay. So you might ask so the techniques we have seen in previous days are, so axions can be generated in the sun. In that case, we use helioscopes to detect, to search for them. Or we can generate axions in the laboratory, and then we can search for axions as main components of the dark matter halo, in the galactic halo. So you might ask how many of these experiments are devoted to these three search strategies, and you see that mainly the experiments are searching for axions in the dark matter halo, and which are the ones here in these red boxes. And as we are in Italy, I can say, start by saying that in INFN is funding experiments that within 3 years should probe an interesting parameter space in the range around 9 gigahertz for a couple of gigahertz, around 9 gigahertz. That is the experimental effort that goes under the name of QUOX, so Quest for Axions. That is a cavity experiment. In Italy, there's also, so these are experiments conducted in the national laboratories, one in Legnaro and one in Frascati. In Frascati, there's also another cavity experiment that tries to, what is typically done in these experiments, you try, as magnets are really expensive and challenging sometimes to develop, you try to get magnets from dismissed experiments. And this is the case for Clash, that now it's been changed, and now the experiment is Flash, because you're using a different magnet. But the idea is that they want to probe the range below ADMX, below the range that the experiment in the US, the first experiment that were on, the first cavity experiment that was run in the US, so it's below, in the range between 200 and 300 megahertz. So that's for Flash at the laboratory in Frascati. And then there's I don't know if you've heard about it, there's a whole center devoted to Axion experimental searches. And that is mainly great infrastructure with ultra-intense magnets and also development of cavities with high quality factors. Then, there's in the US, the first experiment you heard about, ADMX, that reached required sensitivity to probe more specific models, so-called EFZ models. And there's also in Yale, HASTOC. So HASTOC is the first experiment that applied quantum sensing to Axion dark matter search because they succeeded to squeeze noise to improve on the sensitivity, or better, to improve on the scan rate. We will talk about this later. One more, there are also experiments that probe ultralight axions, again in the US, so like Abracadabra. And as for axions searched with experiments that are typically devoted to WIMP searches, I think we can mention both LUX and Angxin in one time. For laboratory axions, there's, let me say, ongoing just one experiment, and it's really exciting time because in a few months, they're starting to run the experiments, will soon give results. And this is an upgrade for a former experiment. So this is what from a former experiment that was called ALPS-1 here. And the basic idea, I said this, you generate axions in the lab, meaning that you source a very intense field, in this case with a field, and in the presence of magnets through a Primakov process, the axion gets converted, the photon converts to an axion that can, due to this feeble interaction with matter, go through the wall and be detected eventually in a second cavity beyond the wall. These type of experiments involve the utilization of, again, quantum techniques. They are going to use heterodyne readout for the cavity, for the signal in the obtained in the regeneration cavity, or even transition edge sensors. Let me also mention another effort. So you have a source when you use the laser, it's in the photons in the optical regime. But you can also use photons, say, in the microwave regime. So you can have sources with gyrotrons at 30 gigahertz and do the same experiments. But this is just a proposed experiment from as much as I know. And it's also challenging due to the use of ultra-intense gyrotrons, these sources that are really, really expensive. We mentioned also the possibility, the ongoing experimental effort for detecting axions from the sun. That is evolution from an experiment that was run at CERN, CAST, the CERN Axion Solar Telescope, and with baby YAXO, as you will see in a while, the idea is to improve the sensitivity through an intermediate experiment before going to the final observatory YAXO, which has the required the sensitivity. In any case, also this baby YAXO appears to be interesting for because there are many physics cases that can be investigated also with this at this intermediate stage. So the experiments that I've shown are mainly relying on axion to photon interaction for detection, and they as for helioscopes, this area that you see named CAST, you see that the limit that is given is independent on the frequency, and it's also a good way of doing this, doing axion search, because it's completely model independent in this case. And you see the projected reach for the helioscope also plotted here. The experiments, the cavity experiments, as you see, all the lines that reach down to this yellow band that has been broadly discussed in previous lectures, are and requires sensitivity that is appears to be available only on these resonant detectors. So if you're resonant, as you can expect, you're more sensitive, but then the search will take a longer time. This is the idea I would like to work on next, on a few next slides. So if we compare these two types of experiments, they have the same underlying processes that are exploited in cavity haloscopes. So in this case, axions generated in the sun get converted in the detector due to the presence of an intense magnetic field, and the fourth power of the coupling scales with the square of the intensity of the magnetic field, and there's also a geometry that for the magnet that plays a role, as you see from the L and A are respectively the length of the magnet, and A is the cross section of the magnet. So the axion get converted into the magnetic field and gives photons that in this case are in the range of a keV. So you, at the end of the day, have to detect X-rays, so also the detection of these photons has to be optimized through a good optics that focuses the photons directly on the detector. And here's why this B factor is the level of noise offered by the sensor. And here are a few numbers to give you the idea what scaling means for experiments. So you can compare directly the former version of the helioscope that was run at CERN, and you see that it's mainly improving on the figure of merit of the magnet, this FM, so the square of the magnetic field and the geometry. So yeah, you're also working on trying to lower the background of the X-ray receiver through this B factor. And you see what I was mentioning, that even with this intermediate scale detector, where the development of the magnet is really the challenge here, beyond other parameters that I'm not mentioning, even at this stage, this baby Axion can probe an interesting regional parameter space. So we're really looking forward to seeing several results from ALPS 2 that was also in this explosion plot. You see that the level that ALPS 2 should soon reach the sensitivity is well below the level that was set by the former helioscope. And in this case, you're working in the optical regime, so it's a matter of improving the finesse, so of the two cavities, this F that we have here, of the optical cavities. And again, this is another experiment in which they are trying to use magnets from former experiments. For readout here, there's a heterodyne technique, but there's also plans to use transition edge sensors, which should not improve on the sensitivity of the readout, but in case of a discovery, it's a good way to change a part of the experiment to better, to obtain another confirmation of the result. So here's for experiments that are model independent and that give a result that is in so flying independent of frequency. Let us now worry about the QCD axion. So all these resonant experiments that address reaching also the most pessimistic models. Here, the basic idea is that the observable is an effective RF field that you are looking for, micro RF depending on the frequency range. And this is related to the fact that below 1 electron volt, there's a fundamental watershed. So if you're looking for dark matter particles that are light, and you take, this has already been mentioned, the value of the local dark matter density, order of 3.4 GeV per cubic centimeter, you can estimate that there are many, many of these particles. They can occupy the same state, and so what you are looking for is a wave at the end of the day. For instance, and the frequency of this wave you're looking for is directly related to the Axion mass through this expression. So let's make an example with 100 microelectron volts. You're looking for a photon at 25 gigahertz. And 25 gigahertz, to give you an idea, if you want to make an experiment, a resonant experiment, a cavity, a box, an RF cavity is a few millimeters dimension. Okay, so it's really also a problem of sensitivity that we have to address here. And another important information is that compared to the conventional search of dark matter with much heavier particles that are looked through scattering processes, in this case you have a wave that is coherent within the dimension of the typical detector. So these are they are so-called tabletop experiments, not just because they occupy the space of a table, but because they are not large, large as helioscope or much larger experiments are. And the number you have here is that if you look for 1 microelectron volt axion, the coherence length is 1 kilometer. So you will find a coherent field in that range. I'm dividing here different ranges of the open parameter space. So the space in which you have seen those lines going down to the sensitivity required to probe the QCD space refers to this range of axion masses, so from 3 up to about 60 microelectron volts. And these are the so-called cavity helioscopes, and also in a version in which inside the cavity we have a material, and the axion can interact with a magnetized material through an axion spin of the electron interaction. So that is the range I will mainly talk about, but I would also like to tell also something about the higher frequency range, so heavier axions. Can we probe them? As with cavities, there's a limit, as we will see in a while. So you can't go above a certain frequency, and it's really, really nice that in the past few months, good ideas have been brought into the lab with experiments that will soon be run. And I'm talking about dielectric helioscope, so the MADMAX experiment at let's run at DAISY together with baby Axion. So there are these are experiments that will be running DAISY. Okay, so let's start to see the next few slides. I'd like to show you a bit how to estimate the speed at which these experiments can be run and where the limitations are. So the basic idea I mentioned of the cavity helioscope is that of having an axion to convert into a photon inside a resonant cavity whose frequency is directly related to the axion mass in the presence of a strong field. So this is the inverse Primakov effect, exploited also in former experiment that I mentioned. And the ingredients for this type of detector are shown here. So for this photon, you provide a microcavity that resonantly amplifies the signal inside the cavity, and requirement is, and I would say is the most difficult job for these type of detectors, to be able to probe more different masses. So the cavity has to be tunable. I have to be able to change the frequency of the resonator. So change the effective dimension of the cavity. And the other ingredient, the central one, is to have a magnet that delivers multi-Tesla fields. So we're talking about fields as high as 8, 12 Tesla. Even though commercially available magnets, superconducting magnets, are there up to 14 Tesla. But in that case, you want high intense field, but you also want these magnets to have a bore in which to host the experiment, large cavities or multi-cavities. This is the challenge sometimes. A central part, as we will see, is related to readout of the signal inside of the cavity. So this is a problem of not only cooling down the cavity to millikelvin temperatures, so the lowest temperatures that are available in the universe, but it's also a matter of using the right technology. And you will see that the difference now and the huge and the big leap that will be possible in the next few years by these type of detectors is related to the recent development in the quantum information science field, where Josephson parametric amplifiers have been introduced, and also other types of technologies and quantum sensing that really makes the difference in this field. We said that it's mainly a resonant conversion, and it is done within the cavity line width. So this Q that you see there is the quality factor of a resonator, which you might, it's given directly by the ratio between the frequency of resonance of the cavity and the line and the width of the resonator. Typically, these have a Laurentian curve, and this is delta F. So it's a measure of the losses, ohmic losses that one has within the cavity. And as you see, the signal is directly related to this quality of the cavity, this figure of merit of the cavity. And of course, again, square dependence of the signal on the intensity of the magnetic field, and takes this CMNL as a number comparable to 0.5. V is the volume of the cavity. And if you take best haloscopes, the numbers for the power is 10 to the minus 22, 10 to the minus 23 watt for the signal that is generated inside the cavity. The problem arises when you want to probe higher frequency range. And by higher frequency range, I mean going above 5 gigahertz, around 5 gigahertz, up to 15 gigahertz, which is a range that these haloscopes can still probe. And this is due to something that you see directly here. So the signal scales very poorly with V, because the frequency of resonance of the cavity is inversely related to the radius. If you take a pillbox cavity, the frequency of resonance of the mode that you exploit for Axion detection is the one that is the transverse magnetic mode, the first one that you try, that you find. And you do see that if it is a 10 millimeter radius cylinder, so 12 millimeters diameter cylinder, the frequency of resonance is 11 gigahertz. So you are already there. You have a very small cavity, and the signal is even smaller than that. Okay, so going higher in frequency means having smaller volumes and smaller signals, and finding difficulties in making a detection. So this is one problem, and another problem in going higher in frequency is related to the fact that quantum noise enters into the play and limits the detection. So, so I'm talking about when you see in this plot, haloscope is within this red line, but it includes the higher frequency range haloscopes that have been recently proposed. So this Mad Max approach with dielectric haloscope and this ALPA approach with, that uses metamaterials for detection of the axion. So let me say just a couple of words on the speed. So we said it's a resonant detection. The signal is much smaller than noise. In these experiments, you're at least 2 orders of magnitude with a signal below Johnson noise, even when you use very good amplifiers in the receiver, which means that you have to integrate the signal for a time Tm as indicated here. So this is the so famous decay receiver expression for noise. You can improve on noise by integrating the signal. So the sensitivity at the end of the day is set by the ratio between the signal, so how you have devised the haloscope, and the level of the noise. You can improve on that, but of course you can't integrate for much too long time. So this typical integration time being hundreds of seconds in a single frequency. Yes?
This might be a very naive question, but I'm assuming that when we measure something for some amount of time, both signal and noise increase similarly. Not one of them increasing with
That is true if it's technical noise, but if it's Gaussian noise, it's a type of noise that makes the difference. In this experiment, Johnson noise is typically white noise, Gaussian noise. So by integration, you can show that you improve with the square root of n, the sensitivity. But if only it's Gaussian. And in fact, when you do the analysis, the first thing to do when you exclude the parameter space is checking if the noise is Gaussian, if the fluctuations that you see are those that are driven by Gaussian noise. So to make the story short, instead of using the power of an haloscope to qualify if it's good and to say about the chances you have for detection and sensitivity, you instead use, instead of the power, use a figure of merit that is called the scan rate. So this df in dt tells you the speed at which you probe the parameter space for a given sensitivity, Ga gamma gamma. And I see that this scales as the fourth power of the magnetic field, and I'm plotting in red the parameters that are related to the cavity. So QL is again this figure of merit, and V is the volume, and then there's a role that is played very strong, as you see, it goes with the inverse of the square of the noise temperature of the receiver, which is mainly determined by the first stage of amplification. So these receivers, these micro receivers, are the same ones that have been used for the cosmic microwave background discovery. So you have many amplifiers that are cascaded, but it is the first one, the first amplifier that sets noise. This sets this Tn. So in this experiment, haloscopes have been equipped with very low noise amplifiers to minimize this Tn. But I want to draw your attention to this simple estimate that you can do. So if you trust me, I'm very optimistic when I say that a best haloscopes scans the parameter space at gigahertz per year. This is very optimistic. So it's much more probable 100 megahertz per year, okay? And These are the given sensitivity we said at KSVZ. So if you want to reach down to the FZ, you will have to run the experiment much slower if you don't introduce a change.
For this, you mean PSVC at the weakest possible coupling?
I'm showing you, so I said, take this number and trust me, and I say, okay, here you are at KSVZ. Now tell me the speed at which your haloscope goes without changing anything, just by integrating.
The same signal from isolation.
Yeah,
But what I mean is that
which is typically set to 5, around 5. Yeah.
the KFCC is a fairly sharp line, but here at C has more width. Well, this is the line.
I mean, if you see,
Here, this squad is E over N equals to 0. This is the line is E over N. Basically, these are the simplest benchmark models. The simple which you can have.
yeah, those are the lines, right? So if you simply do the ratio between the two GA gamma gamma at the FSZ, this could be the square. So this is the speed, the reduced speed at which you would go. So this is few megahertz per year. That's the reason why these experiments are, I mean, in the high frequency side, considered hopeless at the end of the day. And I'm talking about experiments that are run at the also at the standard quantum limit. So the limit that is set by quantum mechanics in readout of the electromagnetic fields, the quadrature of the electromagnetic fields within the cavity. And it's not only a problem of speed. What I'm saying is that I'm showing you how these experiments are tuned. Here you see the inner side of a cavity. It's a copper cavity, the conventional pillbox cavity used in a DMX experiment and also at CAP and in other experiments. What you do, you insert inside the cavity an offset rod that is rotated off axis inside the cavity. This breaks the transfer symmetry and allows for, you see here, tuning the cavity from around 3.4 to about 5.8 gigahertz. But that's not the, but this is the simple picture. What you instead discover when you go in the lab is that when you tune, a problem that arises in this experiment is that since there are many modes inside a cavity resonator, mode mixing may come into play. So the axion-sensitive mode, which is typically a transverse magnetic mode, is impacted by other modes that come that cross in frequency with the axion-sensitive mode while you tune the rod inside the cavity. And this makes the haloscope blind in the range in which these two modes mix. And this is what you get experimentally. So this is when you tune the rod, and this is the frequency range in which you expect to tune. And these are the red boxes that tell you that the mode that you were expecting to use for axion detection is blind because it crossed with another mode which is not axion sensitive. So that's the reason why, to address the high frequency range, researchers in this field have started to introduce completely different types of cavities. So no more the simple pillbox copper cavity, but use, say, dielectric resonators in which you can allow for modifying the shape of the cavity mode. This allows to get two things that you want. One is to go to higher quality factors, as we have seen the signal is directly proportional to the quality factor, so there's strong interest to improve on that. And you get to high quality factors, and I'm saying quality factors that are comparable to the Axion quality factor, order of 10 to the 6. And because, how do you get there? Because you are focusing the the mode, the axion-sensitive mode around the cavity axis and suppressing the losses at the boundary. And this, another thing that is really useful in this resonator, type of resonators, is the fact that you can have large volumes even on high frequency. So somehow you find a solution to the problem of the bad scaling with volume. To give you a number, at 10 gigahertz, a cavity would have a tenth of a liter volume. But with these cavities, you can get a factor 10 better. So two things, higher quality factors and a good effective volume. Another great big step in the field is related to the utilization of superconducting cavities. So up to a few years ago, it was believed that only copper cavities have been used in copper cavities are being mainly used in experiments because of the presence of magnetic fields. So superconductivity that would allow for reaching highest quality factors is not compatible to the Meissner effect with intense magnetic fields. But now, if you properly design the shape of the cavity and use type 2 superconductors, so superconductors that tolerate magnetic fields, you get to a quality factor, again, that exceeds the Axion line width. And you might wonder how these types of cavities are tuned. And okay, this is not compatible with the tuning rod mechanism that I've shown you earlier. And so you start to use clamshell tuning. And by clamshell tuning, I mean that if you are looking at the cavity from the top, and this is the cavity axis, what you do, you prepare cavities that can be opened like this or like this. That way, you are changing the effective radius of the cavity and you get frequency tuning. Of course, this can be done within a certain range. This has been demonstrated up to a few hundred megahertz, which is really interesting in this field. So this is what you, again, I'm coming back to this parameter that I mentioned earlier, the scan rate, the speed at which we probe the parameter space for a given sensitivity. I'm plotting here this figure of merit compared to the ratio between the cavity quality factor and the Axion signal quality factor. So with the copper cavities, we have always been in a situation, if this is the Axion line width, this is the cavity resonator width, we've always been in a situation like the one that depicted here. So the cavity quality factor much larger than the Axion line width. So this 10 to the 4 is the limit for copper cavities. But thanks to these new developments that are shown, you can see that the speed gets greatly increased. This is a log scale, while you exceed the Axion quality factor. So when you reach that, you can also improve on that. And these three lines, sorry, I did not write down what we're talking about. Just focus on this orange line, which refers to using Josephson chromatic amplifiers for readout. The green one is for high electromobility transistors that have been used up to a few years ago. So there's really a strong interest in this having high quality factors and also operate this cavity in the experiments. And one more thing that you can do to maximize the signal in this field is to use magnets. And you see that, just giving you the record, in Grenoble, there's a facility that allows you to reach to up to 43 Tesla but that, of course, is available only in a small volume. You see here a 34 millimeter bore. It's anyway interesting that with hybrid configurations for the magnets, you can reach so high. That was for, so we said quality factor magnets. On that direction, we work on signal amplitude. But what can you do about noise? So the signal to noise ratio, our sensitivity, the sensitivity is set by the design of our oscilloscope, but also on the noise. And as I mentioned, experiments are, this is the preamplifier that sets the level of noise, and experiments are currently run using these superconducting parametric amplifiers. So these are amplifiers that introduce the minimum level of noise. That is one set by quantum mechanics. And at the end of the day, when I said, you remember that I said the scan rate scales as t to the minus 2, where t is the effective noise temperature of the receiver, of the oscilloscope. So you say, okay, I just have, this is the sum between the temperature of the cavity and the noise temperature added by the receiver. So it's internal to the amplifier. The amplifier adds noise to the system. So I just can cool down my system and suppress completely the bosonic computation number of the cavity mode. And this is described by this factor. But when I talk about the effective noise of the amplifier, I get a photon that is added by the amplifier itself. So even though I cool down the experiment, this is an example that I'm making at 10 gigahertz frequency, which is where we want to probe for heavier axions. I go down with the temperature of the cavity. I suppress the photons, the photons from the thermal bath in the cavity, but I get to a level where I get a noise temperature that I cannot suppress by diminishing the temperature. And that is the so-called standard quantum limit. And it is just related to the fact that we are reading out the quadrature of the electromagnetic fields as can be represented through this expression. And these are two operators that do not commute. And for this reason, I should better change operator for readout, which translates to using photon counters. So there's a huge experimental effort in all these experiments to equip the detectors with single microphoton counters. These are devices, as I mentioned, that come from the quantum computing field. And the gain that you can get, if I compare the two scan rates using these devices compared to linear amplifiers operated at the standard quantum limit, is exponential. To make an example, if I'm operating at 7 gigahertz and at 40, and I've cooled down my system to 40 millikelvin, I just see that I can increase the speed by a factor of 1,000, which makes the difference. So instead of 1,000 days, it will take 1 day to probe the same parameter space, just because I have equipped my oscilloscope with this type of readout. And to make this more effective, I'm plotting you here all the noise contributions that you have in this type of experiments. So noise in red is the noise at the standard quantum limit, thermal noise in green, and I said there's an exponential gain, but of course that is, if I do not take into account thermal technical limitation of the devices. And these devices are not ideal, as you might imagine. They have a dark count, meaning that they give out counts even though there's no signal input. And that can be, say, 100 hertz, but down to 10 hertz. These days, we are getting down. I can tell you that 1 year ago, we were at 1 kilohertz, and it appears we are now around 20, 30 hertz. So it's a technology that's rapidly improving. And this is you compare this rate with the rate that will be given by an Axion signal, a KSVZ, and the FSZ sensitivity. You just take the power expression that I gave you earlier, you divide it by the H bar omega. And so, say this quarks experiment that we are running in INFN would have a signal at the FSC at this level, and one could just try and we have already tried to make a prototype haloscope experiments to see if this technology can be applied to the field. So am I right that I still have 10 minutes?
You have it's until 16.
So I still have, I'm half the lecture. Oh, super, super. I was running like crazy. So that is not good.
No, this is
Super.
probably say that at the beginning.
Well, you can stop me whenever I go. I don't tell. When I'm not clear. Okay, so I can spend a few minutes to tell you more about this technology, not because it's useful just for cavity haloscope experiments, but because it really opens a new type of parameter space that can be probed. So it's like really when you have a new technology that makes the difference. And this is happening these days. So if you had a photon counter, we said we could really resume using these cavity haloscope also in the high frequency range when you have to address this comparison with the quantum limit. And let me tell you something about how challenging it is to detect photons in the microwave range. So you know there are single photon counters in the optical regime. And that is easy, let me say, not so easy, but it's easy job because you can exploit photoionization processes for detection because the energy of the photon is high. It's comparable to the electron volt, which is comparable to the band gap in several materials. When you get down to the microwave range, the energy of the photon is order of 10 to the minus 5 electron volts, say this when you are at 5 gigahertz. And to detect such a low energy photons, you have to resort to different mechanisms. And the requirements that you have are even more stringent than the requirements that they have sometimes in this quantum information science. So you need to have lowest dark count rates, much smaller than 100 hertz. They have to be efficient, so you ask for at least 50% efficiency. But the most difficult also feasible thing is that this device has to be usable in the same range, at least, at which I can tune the cavity haloscope. So we said gigahertz. So it should have a large, let's call it like that, dynamic bandwidth, so comparable to the cavity tunability. And then, one more problem here is that we want to address axions, not just dark photons. So when we address axions, we have ultra-intense magnetic fields that, again, are not compatible with these devices that are capable to detect microwave photons. So I'll come to that in a while. And I'm here making the distinction between detecting cavity photons, so cavities, so where you can insert these superconducting devices directly inside the cavity, but what you want to be able to detect is photons that have been generated within the resonator, have been coupled to a transmission line, and then fed to the device at a distance. So you need to have at least a few tens of centimeters distance from the cavity. And this is much more challenging for detection and the devices that you have to rely to are those that are based on the utilization of artificial atoms. So I don't know if you've heard about superconducting qubits. These are, so we have natural atoms, And these are instead atoms that we can design through designing superconducting circuits. So the same type of no, are you making a question? Yeah.
I think I'm quite not an expert at this, so this is probably my question. The problem here is that the photons will get redirected.
So the photon, so you want to detect photons, not not use an antenna inside the cavity to detect an electromagnetic field through a linear amplifier, because you have seen that in that case you have too much noise. This quantum noise is too high for detection of axions. So you say, okay, is there a device in which I don't have an intrinsic limitation? And it is this counter. This counter, the operator is a dagger, which is the operator that counts the photons inside the cavity. And this is, there are no intrinsic limitations. The only ones that you have are those related to the dark counts. So the technical noise in the device that you can improve. Okay, so this device is, say you have a device that is capable to see microwave photons. So how do you see that? We said you can't employ photoionization. You have to use atoms whose transitions are in the microwave range. And these atoms are these artificial atoms. So superconducting qubits operate in the few gigahertz range. And the thing is that if you operate it, and I'm coming to this picture in a while, but just think that here you have this photon that comes from the cavity. It has been translated to an excitation of a transmission line. It's no more a stationary. It's no more a photon inside a cavity resonator. It's an excitation of a transmission line. And I need to do that because I can't have any device inside the cavities due to the intense magnetic field. Can you say that again? I couldn't hear you. A microwave? Oh, these experiments are conducted. I mean, the cavity is at the microwave range, and these are, say this is an artificial atom. Imagine the atom. You have an atom, and instead of having optical transitions, this atom has gigahertz transitions. And that's why you can detect these photons, because you can see if this qubit is in the excited or in the ground state. When it's in excited states, it means that a photon, there was an incoming photon that coupled to an input resonator, and then it coupled to the qubit, brought it to an excited state, and then you can read out the state of the qubit to see if there was an incoming photon. This is the basic idea in this technology. But I'm completely aware of the fact that this scheme is rather, it's rather complex to explain, but if you want, I can tell more about that. So here the basic idea is, this is the artificial atom, this part that you see in blue, it's an artificial atom. You couple it to resonators through these capacitors. This is an input resonator, and this is the output. This is the classical RLC circuit, but without resistance, because these superconductors are made in such a way the losses are suppressed. Because you want to see you want to operate these devices with few photons. So the quantum regime with few photons is only accomplished and controlled in these devices, not only at low temperatures, but also in the complete absence of losses. The only losses that you can afford are those that you have in the substrate. So this is one scheme that says, you see, a device that has been very, very recently introduced, and we recently applied it to Axion detection. And another effort, in part being ongoing also in INFN, is the one that relies on simple Josephson junction. So in that case, you have an incoming photon that couples to the junction. It's more complex than that, but say that the junction switches to normal conducting state when the incoming photon reaches this part of the circuit, and you get a click. And in that case, you have detected a photon. So these are the most advanced schemes today, and and for R&D, what experimentalists are trying to address are a few points. So you have to see if these are really compatible with these ultra-intense magnetic fields that we use in axion detection. And particularly, it's not only a problem of Meissner effect. So the superconductor expels the magnetic field up to a certain critical field. It's also a problem, and beyond that, superconductivity is switched off. The metal goes back into normal conductivity regime if it is, even though it is kept below the critical temperature of the superconductor. But the biggest problem is related to this flux quantum thing. So this is how these qubits are tuned. You remember that I told you we want these devices to be flexible for axion detection. We need to change the frequency of the detector, and that is done by coupling flux that is order of 10 to the minus 15 Weber. So it's really, really a tiny, tiny magnetic field that is used to tune the frequency of these devices. So it's also for this reason that they have to be not only at a distance, but especially protected from magnetic fields by new metal and other superconducting boxes. Okay. And the main question that one tries to address is, am I capable to tune this device at the required speed? So the speed, as I mentioned, is half a gigahertz per year when you are in the range of above 5 gigahertz. Okay, so that's for, let's close the box for cavity haloscopes. So we have seen that there are possibilities to reach down to the FSZ also at higher frequencies that are really, really challenging under several aspects. What happens above that? Well, there are good ideas to go above 15, 20 gigahertz, and there are also experimental efforts, mainly motivated, as we have seen in formal lectures, by the fact that there are good indications from QCD lattice simulations to probe for heavier axions, heavier than those that have been probed so far. And that really has motivated the development of these new experimental efforts. So I mentioned that at DAISY, together with the ALPS and Baby Yaxo, there's an ongoing experiment that plan to cover above this range given in frequency is between 10 and 100 gigahertz. And the idea of this experiment is to exploit the fact that there's a discontinuity for the oscillating field of the axion every time we insert dielectric plates into the haloscope. So, and of course, there's a magnetic field that plays a role in this type of experiment, quite a demanding magnet, because you are developing a specific magnet that delivers a 9 Tesla field in a very large volume. We are talking about 6 meter by about 1.3 meter diameter bore. And inside this bore, you plan to put a number of dielectric disks. And these dielectric disks allow for, if properly controlled, obtaining a boost factor of the signal that in this case, I'm sorry I didn't report the formula, but there's a similar expression to the one that I gave for cavity haloscopes with a pre-factor that gives you the power. And in this case, the signal is order of 10 to the minus 23 watt, am I right? And you need a boost factor order of 10 to the 4 to get a signal. And one of the main challenges in this experiment is to make sure that the boost factor that you have calculated, that you have designed with the simulations, so you use finite element methods simulations as you to understand the behavior of the setup. You need to make sure that this designed boost factor corresponds to the actual realization in the lab, which is not a straightforward task. So to do that, they recently are working on a method to get direct information about this boost factor, so this coherent emission that we get from the dielectric surfaces. And it appears they are going to combine reflectivity measurements from the haloscope and check for the noise in the system. So this is really interesting. And another interesting approach, not exactly in the same range, but covering, as you see here, from 5 gigahertz up to just 20, 30, indicating for 40 gigahertz, okay. There's another type of haloscope, so again, big magnet involved, but instead of using the simple photon as the one that we use in cavity haloscope, here you use a photon that is more complex one that has an effective mass as the one that you have in a plasma. So to realize a plasma is not that has the properties required for Axion detection, again, cryogenics, tunability, is not straightforward, so you rely on so-called metamaterials. Though these are periodic structures endowed by a plasma frequency, whose expression is given here, and directly related between to the spacing between these wires and the diameter of the wires. So this sets the plasma frequency, and it's interesting for Axion detection. Well, it's been thought for that, because you can tune the frequency, this plasma frequency, that is directly related to the Axion mass by changing the spacings between the wires.
So you're saying these wires emulate plasma giving photon?
Yeah, this is I'm not an expert of these, but I understand that this is a simulation of these metamaterials. So these materials that have these properties related to the periodic structures. Yes, this is it's super cool. This is a Wilczek idea, I think. Are you Alex Miller? Yeah, you should have talked about this. Yeah, you do the job now. Okay. No, he's not interrupting. I mean, it's your experiment. So I just, I mean, this is the difference between doing the things and telling things that other people do. So you don't know to the required level, the physics involved. So I'm happy you joined, thanks. So I wanted also to tell something about this experiment because again, it's devised like Mad Max in the range where haloscopes cannot probe axions. Well, it's invading it a little bit, yeah. You started at 5 gigahertz, which is not a good news for us. But let's see if, there are many challenges involved in this experiment. You know that better than me, because when you have to move parts in cryogenic environments, that is really making mechanics at super high level, and sometimes you die on the details. So also the dielectric cavity that I shown earlier, that had been devised several years ago, but it had never been realized. So you have to have good, very good ideas to overcome problems that you find in the lab. And I think this experiment has to, together with all others that I talked about, big challenges, a lot of work on the way to give this exclusion plot at the end of the day. Yeah, maybe you can tell something about the quality factor. I've seen it's order of thousands, right? This quality factor plays a role, right? Yeah. Yeah. Yeah, I was just wondering whether this sensitivity to the FSZ is with already the high quality factor. Meaning? Yeah, but we live in with. Yeah, that's. Okay, so I think that I can close here. I'm aware I didn't tell anything about the low frequency side because not only because I'm more involved in the high frequency studies, but also because it's the place in which I see that there's more interest on the theory side, there's more motivation. And yeah, I think I can welcome questions if you have, and you spend a few minutes now.
Thank you very much. Philip Johnson.
Oh, thanks. I didn't mention that. That's also another, thank you. Thank you. No, that is another very, very interesting experiment that has been proposed a few years ago by David Marsh, And that is relying on new materials, so-called topological antiferromagnetic materials. So topological materials do, I can tell you what I understood, but I'm not the expert here. So these are materials that are insulating in the bulk and they conduct in the surface. Here the basic idea is that they can host axion quasi-particles. So the axion would excite polaritons that then at the surface convert to photons. And these photons would be in the terahertz range, because this is the range where these resonances are expected to be in the material. So hundreds of gigahertz up to a few terahertz. Again, it's the range that nobody can probe, right? And it's it's all a matter of finding the right recipe. And recently, I believe a few months ago, a work has been published on these Axion electrodynamics related materials. And one more thing, being antiferromagnetic is important properties in these materials, because you can tune in the range from a few hundred gigahertz up to a few terahertz just by changing the amplitude of the magnetic field. This is fantastic. For people like me operating in the cavity resonator field, to tune is really the main challenge. You can do a fantastic haloscope, but if you can't tune, it's not an haloscope. And it's when you tune that you encounter the main difficulties experimentally. Because these are, you have to tune while maintaining a high quality factor and in a cryogenic environment. Really difficult. So you use nanopositioners that every now and then get stuck. If they don't get stuck, okay, I don't want to go into these details, but the idea to tune a haloscope just by changing the amplitude of a magnetic field is great. I like very much this idea of the turret. And in fact, I built at our laboratory a system to probe for these axion resonances. It's a terahertz spectroscopy apparatus that you use to see if there are these terahertz resonances in the material. But up to now, I didn't detect anything probably related to the type of material. These are composite materials that are, if they are too metallic, you can't do any spectroscopy, at least in transmission, and you just see the resonances. But this idea of tuning with the magnetic field is there also in the other haloscope I didn't talk about, which has been proposed actually in our lab, which is the ferromagnetic haloscope. This is another way of detecting the axion, even more challenging, in which you still have a cavity resonator, but instead of having the axion interacting with the photon, you choose another particle of the standard model, and you have the axion interact with the spin of the electron in a magnetized material. So you have a magnetic field in this case, which is not ultra intense. It's just there to magnetize a material. Then the axion comes, and again, you talk about an effective field that you can detect in the cavity. So it's what the magnetic field excites is the ferromagnetic mode into the material. So we are talking about frequencies in the range of a few gigahertz. So that has already been used to exclude axions in the range of 40 microelectron volts. But the challenge there is to, again, increasing sensitivity means using the photon counters that I talked about, but also in this case, increasing the quantity of the material that you put inside the cavity. And that is the main challenge, I would say, while maintaining a very narrow ferromagnetic line width. We can meet at the coffee machine at the physics department if you want. I'm joking.
I have one question. So I mean, you mentioned, of course, the CMP, of course, can be measured with sticky radiometers and so on. But could you also use your SMPD because microwave, the CMP peaks at microwave at gigahertz, 20 gigahertz or so. Could you use this also to just to measure now with the high statistics also the CMB spectrum, so to say that just, or is it just an overkill?
You are telling something we really like to do. So to use this device in CMB would really make the difference. That's a great idea. So we're starting to discuss about this with the Matarese at physics department to see whether the idea is crazy or if, but the numbers are, I still don't know the numbers.
We also thought, I mean, we can also use this and one more of maybe Axion to look for the gravitational wave that predicted from the Big Bang, namely the so-called microwave background radiation, which is guaranteed there, and we know exactly at which frequency the peak is. It's at the same frequency as the frequency of the CMB. So, and then you would lead it, so to say, again near a magnetic field, but still. So if you develop this thing, and we have tried in a paper which we have published, we have said, okay, we've seen that a single photon detector would be much better than PK radiometer, and if you develop such a thing.
No, that is exactly what I was saying earlier. I want to tell you something about also to you about this device because it will open new searches that can be done. CMB. Well, Stux is in the range where transition edge sensors can be used. I mean, this device is a good up to, say, 20 gigahertz, the ones that I talked about. Then when you go above, you start to use another device, this test sensor.
Good. So let's have the rest of the discussion at the coffee machine.
Okay? Thank you again. It was nice to stay with you.